Hi there, I'm Bohdan, thanks for joining. Today, you'll learn about the exotic quantum computers that promise to revolutionize the field. And you guessed right. Despite thousands of papers published recently and huge investments, they haven't been created yet. But here we are, the joint group of professors Jonathan Bowen's Big Vashadevsky that aspires to become the first in the world to create scalable Majorana-based quantum computers. Here I take the opportunity to thank my supervisors and colleagues, as well as win with other sponsors and supporters of our research. In simple terms, Majorana fermions could be understood as halves of electrons. If these key ingredients are present in a 1D semiconductor, the system could transfer to the so-called topological regime, with a zero-energy state protected with a gap from other states. This state is degenerate in fermion parity. If there is an odd number of electrons, one of them is split into two Majorana fermions, localized at the ends of the nanowire, forming a so-called Majorana zero mode. Remarkably, because of the protective gap and the large distance between the quasiparticles, they are virtually immune to decoherence. Moreover, due to their unique quantum statistics, it is sufficient to sequentially exchange them to realize non-trivial quantum gates. Most of the previous experiments relied on indium arsenide or indium antimonide nanowires with aluminum shells. Despite considerable progress, such architectures offer limited capabilities of scaling up. Our approach is different and rather uncommon. We epitaxially grow semiconductor heterostructures with quantum wells, capped with aluminum. This design is inherently scalable since the aluminum layer could be patterned into any network of gates to define 1D channels in the quantum well. Interestingly, the question of optimal aluminum growth conditions is almost not addressed in the literature. The identification of these growth conditions is my main contribution to this project. Particularly, we aim at efficiently growing flat aluminum layers and special 3,5 buffer layers at sub-zero temperatures at an optimal growth rate. For this purpose, we characterize the surface morphology and cross-sections of our samples with numerous techniques. We report successful growth of 10 nanometer thick aluminum layer on indium gallium arsenide with a size of flat surface regions on the order of 10 micron, shown in the atomic force micrograph. The transmission electron microscopy and electron energy loss spectroscopy confirm both the flatness of aluminum layer and sharpness of metal semiconductors interface. Our current goals are to further optimize aluminum growth rate and carry out the similar research with antimony-based compounds. This will lead to the first comprehensive study of this kind, and most importantly, will bring us a step closer to the quantum computer revolution.